Welcome to another video by electrification enthusiasts. We are doing an unofficial crash course on Simulink. This is going to be crash course number 1 because there's a lot to go over, and we're going to start with some of the basics. What we're going to talk about today is 1, Simulink is time-based, and integration is a fundamental part of a time-based simulation. So we'll discuss that. We will discuss very basic things such as what is a source, what is a sink, the different types of ways of visualizing your data, and basic modification of the signals. We will also get into a lovely little visualization of why three-phase power is amazing, and we're going to use vectors and scalars to do that. And then we'll very briefly touch on continuous versus discrete domain modeling. So that's what we're going to go over today. This is just to show you what we're going to go over. We always build everything from scratch typically so that you see how to do it when it's a crash course, that is. And we're going to assume, in this case, we're not even going to assume you know what Simulink is or how to open Simulink. So let's save and close this. We're going to assume you know how to open MATLAB. In MATLAB, under Home, here is the Simulink button. So click that. It will bring up a list of templates that you can start from. These can be useful. Just do a blank model. And now you have the Simulink Canvas open. So this is the generic simulation environment that MathWorks provides with their tools. This will give us access to things like Simscape Electrical so that we can model electrical circuits, but it also gives you access to Simulink. And Simulink is a very comprehensive, but also basic Simulink environment at the same time. Simulation environment at the same time. For example, you can do really basic things. I just double click and I can type in a block name I want. So I can bring in a step. And I can also bring in a scope. And I'll show you where to find these. And I can connect them. And this is the basic of Simulink. I'll press space to zoom in. It's a graphical programming or a graphical modeling environment. And this is called a source. And this is called a sink because the signal starts here. And the signal is terminated here. And you can see that based on the arrow. And so sources sink is sort of the fundamental terminology Simulink uses to have signal flow. And the first thing you want to do with Simulink is run a simulation. So here you have your stop time and your run button. If I click that run button, it'll run the model. And I will get to visualize this step in my scope. So here is that step function. Make it a little bit bigger so you can see it. Not particularly exciting, but it's basic. Now, if I want to get access to all of the different blocks available to me in Simulink, I go to this library browser button. And this will bring up, there's a lot going on here, so just bear with me while I break it down for you. Over here is the list of libraries. The Simulink library is the fundamental building blocks basically available to everyone. Now, if you know how MathWorks likes to do things, they make a whole lot of these other toolboxes available. So if you happen to have access to an enterprise license or just a lot of licenses like I do, you will have a lot of extra toolboxes installed. But all we want to think about is Simulink. And this is the list of all of those libraries in Simulink that you'll have access to. Now you'll notice at the very top, they have this commonly used blocks section. And if you look here, you can actually see here's that scope function that I was using to visualize things. And it's got bus creator, bus selector. We'll talk about some of these. A lot of these we're not actually going to get into yet, but we'll touch on, actually we won't touch on constants, but they're fairly straightforward. We'll focus more on integrators and gain blocks. But if you remember, I was using the terminology sink and source. If you look down here, Sync and source are two libraries within the fundamental Simulink library. So you can go to sources and you have all of these different blocks that you can use as signal sources. And we'll definitely take advantage of these. The sine wave one is going to be particularly useful for us. Another useful one if you're into power electronics is stuff like pulse generators. And then we also have the sinks here. And so sinks are predominantly used to either display or log data. You don't have to sync any signals. There's a terminator block if you want to keep everything clean, but the model can run without any syncs, but you typically have to have a source of some sort so that there's a beginning. And we're going to show another sync. We'll do it from here, which is this display. So I can click and drag this over here. Before I typically, because I do this a lot, I'll double click and type in the name of the block I want, but you can also click and drag from that library. So when you're newer, you're going to click here, look for the block you want, and drag it in. And then as you get more comfortable, you'll start typing in. So I want to run this wire here. I right click to tap off. And what you'll notice if I hit the run button, this shows me the final value. Whereas with the scope, I have to double click into it, but when I double click into it, I see the entire history of the signal. And so most cases, this is actually more useful because the whole point of Simulink is that it is a dynamic simulation. It's based in time. You're not just looking for the final answer, you're looking for the system performance as a whole. But if there are cases where you do just want to see what the final result is, or if your simulation's really slow, this will actually update live. This model is just too fast for you to see it change while that's happening. And so you've got a source, you've got a sink, and then in between, you do all of your modeling or your logic or analysis, whatever you want to do with Simulink, you do in between. Now we're working towards doing things like putting electrical circuits and those types of models in here. But you can do something really basic, such as a gain block. So I'll go back to Library Browser. This is in commonly used blocks, I believe. Yeah, gain. It's also, is it continuous? No, it's actually a math operation, probably. Yeah, under math operations. This is a really useful library to look at. There's lots of different math operations. Gain is one of the basic ones. So again, I can right click to tap off, and I can take this signal and I can multiply it by 2. You can actually edit this value from the canvas. You don't have to double click and go in. And a nice thing about scope is if I click and drag a wire to it, it'll automatically create a port for me to add to it. So I can have 2 signals on that scope, and then I'll bring another display down here, right click, tap off again. And now I have my original signal, which is ending at 1, multiplying by 2, it goes to 2, that's to be expected. I go to my scope, I can see both signals. They're scaled at 0, they're the same, 2 times 0 is 0. But then when this signal goes to 1, this signal goes to 2. Another nice little thing is if you click here, you can expand your number of axes. So layout, select how many you want, and it'll expand them. And I'm just going to resize the Y. So now they look the same, so you have to pay attention to what your axis value is here to see, oh yeah, they are doubled because I'm not overlaying them. So depending on what you want to do, you can overlay them or have them separate. This is just the bare bones Simulink. You start with a source, you modify the signal, and you pass it to a sink to visualize the data. So now let's talk a little bit more about the fact that Simulink is time-based. If we go to this math operation, absolute values, adds, divides, gains, dot products, min, there's a lot of signals here, or blocks here, that are just fundamental programming blocks. So when you're using these, it's really like we're just graphically programming with Simulink. But if we go to this continuous domain library, we'll see a lot of what for Simulink are basic building blocks that are in no way a fundamental building block for a programming language. Now, obviously, you can do all of these with a programming language. Simulink is built on a programming language. But things like derivatives, integrators, transfer functions, all of these fundamentally need to have a concept of time to exist. And we'll use integrators to start with. Now, we can take a constant value and we can integrate it. Now, if you know what the integral of a constant is, it's a ramp. And we can give this a real-world conception. So I can take this wire, I can call it acceleration. And if you integrate acceleration, you get velocity. And if I integrate velocity, I get position. Notice I'm taking the time to make things look a little nice because that does pay off. So now I have a model that's taking this constant as my source, and I just commented it out, and I'm integrating it. So I should get a straight line, another straight line, but it's going to have a slope. This will have a slope of 0, this will have a slope of 1, and then this will be a parabola. I double-click the scope, and I can see that that is indeed the case. Right now, it's listing those signal names here. If I were to right-click, go to configuration properties, I can turn on a legend, and it will take those values and actually list them up here. And again, I can also split these up into 3 separate. And this is not the greatest slope, so I may want to draw a line and ensure, yep, that is definitely a parabola. It is not a straight line. I can't make a line that lines up with it. Whereas if I go down to velocity, this is indeed a straight line, and obviously this is a constant 1, so this is a straight line. So we're getting what we expected. Now, some things to know about this. I'm using an integrator here. If we go to the library, there is a derivative block. There are times when you do want to use this derivative block, such as with PID controllers. The way Simulink's solver engine is set up, it is always better to use an integrator block and not use a derivative block. So if you have something written such as, x dot equals f of x, and you want to use the derivative block over here, it's better to instead write the equation as x equals the integral of f of x and use this block to solve the other side. Now, with most of you, because you're going to be using something like Simscape Electrical to do your physical modeling, and you're only going to use these type of blocks if you're building a PID controller from scratch, that probably won't ever be an issue, but it's good to know that you want to avoid the derivative block as much as possible and use the integrator block as much as possible. It will give for much more accurate, stable results and faster simulations. All right, so now that we've done that, let's start talking about how to do some signal routing with Simulink. Right now, each one of these is an individual scalar. And I mentioned we're going to display why three-phase power is so wonderful using vectors. So I'm going to use that sine wave block that I mentioned. It's just throwing errors because I am, it's prompting for an initial entry, and I am clicking too fast that it's just using its default value. All right, so I have 3 sine waves. So let's make a 3-phase system. I'm not going to pick an amplitude or a frequency because there is no one amplitude or frequency that'll make every country happy, but every country can agree on 3-phase power. So phase A, we're going to have be 0 radians. Phase B, we're going to shift 120 degrees. So when I do that, I always just write my degrees and then do times pi divided by 180. I find that to be the simplest way when writing stuff in degrees. And so phase C will be 120 times pi divided by 180. Now I can put all of these in a scope as is. And so this is what we've been doing already. And hit run. And we'll get a 3-phase system. So that's fine. But let's start doing a little bit more with vectors and scalars. So there's this thing called a mux block. Number of inputs, I want 3 inputs. If I ever get that wrong, I double click and control it in here. I'm going to connect that here. This block in the library is under signal routing. So there's lots of useful blocks here to let you better organize your model. This mux block is particularly useful because it lets me easily create vectors or split them into scalars. So as before I was working with 3 lines, I am now working with a single line, but it still has all of the data. And now if I was going to do a modification that applied to all of those, such as that gain block, I don't have to do it for each line, I can just do it for one. So this is a good modeling practice, is when you're doing the same thing to signals, combine them and do it as a vector operation. It's actually more efficient as well. But this gives us a good opportunity to display why 3-phase is lovely. You may or may not have noticed when I had the math operations open, some of these were specifically designed for vector operations, like a product of elements. You can see down here, barely, the sum of elements. So we're going to use this block, and this is going to take these 3 signals and add them together. So this is, we'll call this phases ABC. We'll call that sum of phases. And when you sum the phases, this is a balanced system, so they cancel out. You get 0. This is why a balanced 3-phase system is lovely, because your summation of currents is 0. Now, in reality, you have to deal with the fact that things are never 100% perfect, so you rarely get to assume it's perfectly 0. But the fact that it's close to 0 makes dealing with the common mode current or ground current much more tractable than if they didn't sum to 0. So that's really convenient, but there's something that is also incredibly important, especially from the generation perspective. And that's if we do a sum of elements, and let's square these values. Now you may ask, why am I squaring these values? I'm squaring these values because power is proportional to the square of your voltage or current. So you remember, it's either like V squared divided by R or I squared R. It's scaled by your resistance, but it's proportional. So this isn't calculating our power, but this is calculating a signal that is proportional to our power. And whereas this signal was basically a constant 0, this signal is a constant non-zero value. And that's incredibly important, because if you ever get into the dynamics of, let's say, a single-phase motor, they're not particularly nice because you can't actually have constant power. But with a three-phase motor or a three-phase generator, you can essentially have constant power on the electrical side, which means you have constant power on the mechanical side, which means things like torque ripple and other such dynamic effects are greatly minimized when you compare it to a single phase or a two-phase system. And so the sum of the signals is essentially showing you what happens with the currents, and the sum of the squares is essentially showing you what is happening with the powers. And so this is why three-phase power is so lovely. And this demonstrates how we can do something to a vector, and we can take that vector and convert it back to scalar. We can also demux it. If we ever wanted to get the signals back, I can just put them in a demux and tap off of them like this. And if you ever don't know how many signals you have, you go up to this debug tab and you go to information overlays. And down here, you can turn on signal dimensions. And now it'll tell you how many signals are in a particular wire. So I combined 3 into 1, so I'm seeing 3 here. Notice there's no number here. Where's the number? It doesn't show you the number if it's 1. So if you see numbers, you know that where you don't see numbers, it's 1. And if something's wrong with your model and it doesn't actually line up, you'll probably see a question mark because something might not work. If you say something should have 4 inputs, but you only provided 3, it might be confused. And that's pretty much all to talk about here. This can obviously be taken a lot further, but we're just trying to get you a taste of how you can do all this stuff. And so the final really important piece to think about with Simulink is the fact that you have continuous domain and discrete domain systems. And when you're first starting out, that's probably not going to be important. But if you ever do anything that you really want to be used in the real world, there's a high likelihood that at some point you'll be doing something in a discrete system. Because if you ever use a microcontroller, an FPGA, anything like that, you're going to have a clock in your system and it's going to be fixed step. And so let's show you what I mean by discrete versus continuous. This block has a sample time of 0. When you see this in Simulink, a sample time of 0 essentially means continuous time. You can never put a negative time in it because that would mean it was going backwards in time, but you can put a positive value in here. And that will change it from continuous time to discrete time. You can even see that the icon has changed to represent that. And if I run this model, you'll be able to see that the signals are different. And the continuous time one is the yellow one, and this discrete one is blue. And this is particularly relevant because when you have an embedded system, it has to take in its inputs, and then it has to do a calculation before it can update its outputs. So there's always a time delay with a discrete system from the inputs coming in to the outputs being updated. And Simulink lets you capture that delay with discrete systems. Now you can do this using logic. You can actually do this if you do it more like a classical controls approach. They have Z-domain, not discrete. They have the Z-domain blocks. So you can do it with Z-domain blocks, or you can do it more with just unit delays and basic logic, depending on what you're more comfortable with. I do recommend learning the basics of discrete classical control or discrete time signal processing because it will open up a lot of doors. But this lets you step into that world because Simulink can mix and match continuous and discrete time systems. They can be included in the same loops. And something that's really useful once you start doing that is this button right here. The 2 arrows. This turns on your timing legend. So you can see which signals are continuous and which ones are discrete, and you can do multiple rates. So I could make this one a little bit slower. I'll hit Control D to update, and I'll get a different time for each discrete rate. This gets really relevant if you ever start getting into advanced systems where you have different parts of your algorithm running at different rates, or if you're using systems on a chip, especially if you're just putting something on an FPGA, something on a processor. This starts becoming very important. If you're just doing, schoolwork, if you're a student, there's a much higher likelihood that you can get away just leaving everything in the continuous time domain. But if you're taking a controls course, they may ask you to intentionally go to the discrete time domain, the Z domain, for those reasons. So that's all I'm going to talk about for this particular video. This is just one of many updates I'll do specifically on Simulink. There's going to be a lot of things to talk about as far as organizing models, going deeper into some of the blocks that are less intuitive. And so I'll do that. And again, as always, please leave questions if you have questions.